In the records of scientific history and the scientific revolution, there was Sir Albert Einstein. His theories reshaped our understanding of space, time, and the cosmos. He gave humanity a whole new way to look at science. Among all of his works that he had done, there was one enigma that troubled him deeply: quantum mechanics. Why was Albert Einstein worried about quantum mechanics? What made his mind think quantum mechanics is incomplete? On May 15, 1935, Sir Albert Einstein, along with Boris Podolsky and Nathan Rosen, published a paper from the Institute for Advanced Study, Princeton, New Jersey. The title of the paper was, "Can Quantum Mechanical Description of Physical Reality be Considered Complete?" There are reasons for which he thinks quantum mechanics is incomplete. Einstein said any serious consideration of a physical reality must take into account the distinction between the objective reality, which is independent of any theory, and the physical concepts with which the theory operates. In simple terms, to properly understand a scientific theory, it's important to recognize the difference between the real world, which exists independently of any theory, and the concepts used in the theory to describe this reality. We use these concepts to form mental pictures of the real world. The statement highlights the need for scientific theories to accurately reflect the objective reality they seek to describe, using concepts that help us visualize and understand that reality, ensuring that scientific theories align with observations and measurements of the physical world. The correctness of any theory is judged by the degree of agreement between the conclusions of the theory and human experience, by performing the experiments and analyzing the measurements. Therefore, every element of physical reality must have a counterpart in the physical theory. The element of reality must be found by an appeal to results of experiments and measurements. The definition of element of reality is this: if, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Now you know some criteria of physical reality, required when looking into a theory to prove its physical description. So let's deep dive into why Einstein thinks quantum mechanics is incomplete. The fundamental concept of quantum theory is the concept of quantum state, which is supposed to be completely characterized by the wave function psi, which is a function of the variables chosen to describe the particle's behavior. You need to realize that quantum mechanics plays different rules when compared to classical mechanics. Classical mechanics works really well in the macroscopic world, but as you go on to work in the microscopic world, the same mechanics or rules don't apply, which is why quantum mechanics and its theories justifies what is happening to the microscopic world, the world of atoms, molecules, quantum field, etc. Einstein demonstrated in his paper that quantum mechanics is of statistical nature and not deterministic, using the Heisenberg uncertainty principle. There is a famous line he said in 1945 that says, "God doesn't play dice with the universe," and that God tirelessly plays dice under laws which he has himself prescribed. That was his response to quantum mechanics' weird, non-intuitive rules. Coming back to the point, Werner Karl Heisenberg found an underlying principle which is not due to uncertainty in the measurement of a variable of a particle by equipment, systems, etc., but an inherent uncertainty in the act of measuring a variable of a particle. The principle states that the more precisely the position is known, the more uncertain the momentum is, and vice versa. This principle works only for complementary physical quantities, such as position and momentum, and also works for energy and time. The more precise a physical quantity is measured, the more uncertain or less precise will the other complementary physical quantity with respect to the first one. The precise knowledge of one of them precludes such a knowledge of the other. These complementary physical quantities, such as position and momentum, are sort of like a seesaw when one goes down, resembling more precise of the true value, and the other goes up, resembling less precise of the true value. If you ask me why it is like this, it is all because of the particle's quantum property, that is, the particle-wave duality. The particle possesses a point mass and a wave-like properties. Well, if you compare to position and momentum properties, it resembles the characteristics of point mass at a location and wave carrying the momentum of the particle, respectively. A detailed explanation of this will come up in one of the upcoming videos. From all this follows, Einstein made a conclusion. Either 1. The quantum mechanical description of reality given by the wave function is not complete, or 2. When the operators corresponding to two physical quantities that do not commute, the two quantities cannot have simultaneous reality. I think you did understand the first one, but may not be the case for the second statement. To put simply, the operators mentioned are just like the position and momentum quantities, not being able to measure precisely both simultaneously. If both of the quantities had simultaneous reality and had definite values, these values would enter into the complete description according to the condition of completeness. If then the wave function provided such a complete description of reality, it would contain values which would then be predictable. This is not the case according to quantum mechanics. This puts into a contradiction to those previous statements, that either one of them is true and not both. Okay, now we know that one of those statements is true. Which one is right and wrong? To answer that, let's take a different directional approach. It is said that in quantum mechanics, it is usually assumed that the wave function does contain a complete description of the physical reality of the system in the state to which it corresponds. At first sight, this assumption is entirely reasonable, which is that the information obtainable from a wave function seems to correspond exactly to what can be measured without altering the state of the system. That is, the wave function holds the information which can be obtained and does show probable outcomes to what happens after measurement, which is predicted without altering the system. Now, taking into account that this statement is true, let's take an experiment. Let's take two systems, System 1 and System 2. Let's take two systems together and let them interact for a period of time t, after which we suppose there is no interaction between the two systems. We further suppose we know the states of these two systems separately before their interaction at time t equal to 0. With the help of the Schrödinger equation, we can find the combined state of these two systems for any subsequent time. For time greater than time equal to t, let's designate the corresponding wave function by piece I. After these systems interacted, we cannot calculate the state of either one of these systems left after their interaction. According to quantum mechanics, this can be done only with the help of further measurements, by a process known as the reduction of the wave packet. In quantum mechanics, it is also called the collapse of the wave function of the system. Let's consider both the systems having only 1 degree of freedom each, and let's take a translation of one of the three axes, that is, along the x-axis. Any physical quantity we take to understand a system there is an operator having a corresponding function, and sometimes a value too. Operators in quantum mechanics are mathematical entities used to represent physical processes that result in the change of state of the system, and also used to extract information about any measurable parameter from a given wave function. Here, the function and value that we call in quantum mechanics is eigenfunction and eigenvalue. When looking into functions of the operator momentum and position, they have corresponding traditional eigenfunction and non-traditional eigenfunction respectively. In general, as a rule, a traditional eigenfunction of an operator is a special function that, when operated on by the operator, produces the function itself multiplied by a constant. This rule works for the momentum operator, but not for the position operator. The position operator acts on the wave function to extract information about the particle's position, just like the momentum operator. However, the position operator does not have eigenfunctions in the traditional sense. Therefore, the position eigenvalue is not local or a constant, rather it shows probabilistic positions, meaning the position is dispersed over an area of the function. This is one of the conclusions that lead into the beginning on why the quantum mechanical description of physical reality be considered complete or not. A question, a debate, came into the world of classical mechanics in 1935. So, what we have covered from Einstein's paper is about halfway there. What is left is an experiment where he concludes why quantum mechanics behaves just the way it is. What Niels Bohr and Erwin Schrödinger had to say about his paper is very interesting. So, to know more about that, do follow for Part 2 video.